Okay, sorry about that. Can you hear me now? Please give a thumbs up or reply. Ah, super. Okay, thanks. And good that you're here. That's okay, so I have a few questions for you that I sent them around, so you thought about it. So maybe we can go quickly through them. So first, what is the difference between Stokes and anti-Stokes Raman scattering? Go ahead, just.
Stokes scattering, the incident photon has a big wavelength, yeah, and the anti-Stokes is smaller wavelength, less energy. It starts from the
No. Yeah, so no. Yeah. So what we usually draw these things as Jablonski diagrams. So these are diagrams of energy levels. Would you care to draw it or? Fresh one.
So in the, this is the ground state.
Yeah.
So in the Stokes Raman, we have this transition, and then this one. In the anti-Stokes is the start from this level.
Yeah. Okay. So let's thanks. Let's try to refine this. So can you all see the drawing? Or, yeah. Okay. You online cannot, but we'll fix that later. So this would be the ground state. So make this a little bit thicker. So what about this state? What kind of state is this? Yeah, it's not a real electronic level, but something that is in between. So I'm going to make this into a dotted line if you allow me. So an upper. So let's call this S0. That's the usual convention. Call this S1. That would be somewhere here, let's say. And then the virtual level is somewhere in between. Okay, what are these levels? Yeah, these are vibrational levels associated with them. So what happens in the Stokes Raman is that the compound is excited to this virtual level, and it falls back to some vibrational level. And what you said is exactly right. So this is more energy. This transition is of higher energy than this transition. Transition. I'm sorry. What was again the relation between photon energy and photon wavelength and energy? Yeah, so that is inversely proportional. So if you lose energy here, then you will get a longer wavelength. If you gain energy, then you will have a shorter wavelength. So that is, and that is exactly what's happening here. Here, the molecule or the compound is already at an excited vibrational level. Is excited to this again to this virtual state, and then falls back to the ground state. So net energy is gained, which results in short wavelengths. So which of these two processes is more probable? Why?
Also statistics. So we have molecules more likely to be in the ground state than in the excited state.
We're going fast, and that's exactly the right answer. Just because of that. Okay, then just to see if that question is on there. No, it is not. So how fast is this process?
It's 1 per million.
Yes. Okay. What a giveaway. That's a long time. It's almost because the states really do not exist. It is almost instantaneous. So if you really would have to pin a time on it, then I would say like nanoseconds, picoseconds. Very short. So fluorescence of okay, let's order them. So we had fluorescence, phosphorescence, and Raman. These molecular transition processes could occur. So what time scales? So if you would order these processes in time scale, so let's say shortest first and then longest last. So how would you order them?
Phosphorescence is slowest, I think. Like on a scale of microsecond. And on fluorescence.
Yeah. And then Romano I already gave it. So you know this glow in the dark sticks, right? Which you break and then they glow. That can take minutes. That is phosphorescence. So phosphorescence is really something that is a process that can take very, very long. Fluorescence is somewhere in the middle that can take from microseconds to milliseconds. That depends a little bit on the molecule. And then Raman, simply because these virtual energy states do not exist. It is really instantaneous. Okay, so you already had the correct answer to what the Raman efficiency was about. What did you say? 1 in a million. Yeah, I think that's a generous estimation. It's perhaps even a little bit lower, so 10 to the -8. So again, exactly what was an efficiency?
Is the ratio between the powers?
Yeah. So if you would translate that into this picture, that would mean. So yeah, the ratio between powers, that's correct. But if you would translate that into the Raman picture, so what would a Q Raman mean? Yeah, go.
I think it's the ratio of the scattered photons to the photons.
Yeah, that's true. And in this case, so in this case, it means the ratio of the photons that are actually transferred into Raman photons.
Yeah.
Yeah. So for we had the scattering efficiency that told us how much power was converted or scattered away from the incoming beam. Absorption was for the absorption efficiency, it was the ratio of the powers that was gone, absorbed. And for Raman, it then means that it is the number of photons that is, or the percentage of photons that is Raman scattered. Okay, some other fundamental questions. So if you have, let's say we have this Q Raman of 10 to the -7, how would you translate that into a Raman scattering cross-section and into a Raman scattering coefficient?
The cross section is the efficiency times the cross section.
Yeah. Yeah. So for the so basically the same thing for as for a molecule. So we have let's say sigma. I'm not going to sublabel it because it's valid for all of them. Is the Q times the geometrical cross section. And then for the coefficient. So what was so we had so basically we're scaling up. We started out with an efficiency that we converted that into a cross section. But now the question is what about mu? What about mu?
It's rho times the sigma.
Exactly true. And then of course the question is what is rho?
Rho is the density.
Yeah, that's the density of the Do you know what? So this is a percentage that has no units. That's just a number, pure number. G is a cross section, so that has units square meter, which means that sigma will also have units per square meter. So down here. So do you know the units of these two parameters? What is the unit of mu Raman? Okay, so the slide.
It's 1/meter.
1/meters. Okay, and then rho.
It's a volume, 1/volume. So
1/volume. Yeah, exactly. So rho is the number of particles per unit volume. And then yeah. Okay. Now then, the fourth expression. So I've just written a statement there. The average Raman length, average length, subscript Raman, is given by 1/mu Raman. Mu Raman we just discussed, and it's about 1 kilometer. What are your thoughts about this statement?
Well, if you write it as an exponential expression, then the Raman length, L, would be the characteristic length after which the intensity has dropped by a factor of E.
So L, and then the whatever the intensity is, will probably follow some kind of exponential decay. If this is 1, if this is 1/E, and then here we are at 1/U. Yeah, that's true. Okay, so but that was the second part of the expression. Oh, the middle part actually. That is what mu means. So what does it mean that L Raman average is 1 kilometer?
The interaction is very rare, hardly ever happens.
Yeah. So if you would have a hypothetical medium of I don't know, a few kilometers wide, which would Raman which would be Raman active, then on average a photon would have to travel 1 kilometer before it would ever be Raman scattered. That is what the interpretation is. Okay. I'm not exactly sure if Johannes mentioned the acronym CARS, Coherent Anti-Stational Scattering. So, okay, what is it?
it's like a mechanism for making the anti-Stokes Raman scattering more likely to happen.
Yeah, that's true.
Using like multiple photons, thus exciting the molecule to the vibrational states after the vibrational states. Just making the anti-Raman scattering.
Yeah. So let's start with if I would look at simple anti-Stokes Raman scattering, I would have a little bit bigger. I would have a ground state here, vibrational excited state here, and some virtual state here. So what happens now? What are we doing?
First photon will excite ground state to this virtual level.
Okay. So like this. And then next.
Then we will decay of the upper vibrational state.
Okay. And how does that work?
Emission.
Yeah, that is the trick. That is the trick. So you have a laser beam that pumps up photons to this or pumps the energy level to this virtual state. So the pump beam, and then there is a dedicated laser beam that stimulates emission down to this vibrational level to get that populated. Basically, how a laser also works. That is called the Stokes beam. And then what? So now we have this populated vibrational state.
And this probably excited even further to another.
Yeah, exactly. Then just the let's say the classical anti-Stokes process takes place. So we have excitation, which could be to any level, but at least a new virtual level, and then from there it drops down again. This is the pump. This is the probe. Beautiful. Yeah.
Because you use a photon to do this direct emission thing, but how do you know that photon does not excite the atom or compound even further to an even higher energy state?
Yeah. So what you usually do is that you already know approximately what the energy level is that you want to probe here. So you can pick it. So what you have to do first and foremost is to pick the energy difference between these two, so that you actually stimulate populating this one, and then it depends a little bit. If you expect that there are higher energy levels living here, then you should be careful in selecting the probe wavelength. But if there is not, then you can just use the pump wavelength again for efficiency. So it depends a little bit. So usually you have to put in some knowledge of the molecule that you want to measure already to get this done. I have a question. This is just something to calculate. So before COVID was a big problem. Malaria was a big problem. So that this question relates to that. What happens if a person gets infected with a malaria parasite is that the hemoglobin, so the oxygen carrying protein in the blood is being and is being converted into hemozoin. And one way of detecting malaria or diagnosing malaria is to actually probe this hemozoin molecule. And people have researched for quite a few years now to do that with Raman spectroscopy. So to make a small, I don't know, setup or a microscope that you can put in a clinic somewhere in a country that is infested, and then take a little blood prick, take a little drop of blood and see if the hemozoin is present there. And then you would diagnose it. So what we know of hemozoin is that it has a Raman peak at 1371 inverse centimeters. Can you now calculate for me what the Raman emission wavelength would be? Stokes Raman, so not anti-Stokes, Stokes Raman. If we would use a 780 nanometer excitation wavelength. That is something that we can easily buy because that is used in laser pointers and in etc. So this could provide for a cheap way of diagnosing malaria. But now the physical question. So again, 1371 inverse centimeters is the Raman peak. This emission wavelength, what is the excitation wavelength? If you already did it, you can write out the answer for me. That's also fine. Ja, ja, wat gaan we doen, hè?
I'm not sure, but my answer is 860. That's the answer.
To be true from the top of my head, I do not know. But if you want, or if just explain the reasoning and explain that. Ja, kom op jongens, het moet een beetje interactief zijn dit, hè? Zit niet op Zoom. Kom op.
So first I do this 1 over the citation wavelength, and then I subtract the shift from it, which equals in the end and the corresponding wavelength to that is just its inverse, which is 70 nanometers.
Does anyone disagree? Okay. No, we're fine. Yeah, this is exactly this way. So the formula was 1 over lambda shift is 1 over lambda excitation minus 1 over lambda emission. Should be the other way around. It's the other way around. Yeah. Emission over excitation. You can calculate. Raman is not really my expertise. A little bit bluffing here. Okay. Oh, it is. Yeah. So X. So let's move to OCT. Johannes talked about it. And one of the necessities, one of the things we needed was a low coherent light source. What exactly is a low coherent light source?
So the light source with a lot of different wavelengths.
Yeah. So, so can you give an example of such a light source?
Sun.
That's the best example ever. Yeah. Yeah, the sun. It has a lot of different wavelengths. Of course, if you then narrow it down a little bit, you would get to halogen bulb or something like that. But you can also make lasers that support multiple wavelengths. Of course, for practical reasons, we prefer lasers over the sun, but yeah. Okay, so then two different modalities of OCT were discussed, so-called time domain OCT and spectral domain OCT. Do you know what the difference is between these? Why are they called this way anyway?
Well, I think in the time domain, you fix you want one specific wavelength and then you vary the distance. In the spectral domain, you keep the distance fixed, but you have a wide range of wavelengths. At the coherence way going through the.
Yeah, that's almost true. So the small correction is that for time domain OCT, you have all the wavelengths, but the distance is fixed and moving. So the light source emits all the wavelengths at the same time, but you move a mirror to sample different positions. And for spectral domain, you would have either a fixed mirror and have all the wavelengths coming one by one, or you would detect them separately. Makes sense or not?
I think the latter was the thing with the greater.
Yeah. So the confusing thing about this is that there is two ways of doing spectral domain OCT. One where you have the wavelengths one by one, and one where you have them all together. So if you would start with a laser source with an interferometer, so you have a beam splitter here that splits the light. One part goes to a reference mirror here. The other part goes to something that you want to measure, sampled, and then light is going in, getting out, reflected again from this mirror, which you noticed from Johannes's assignment, of course, is that half of it goes back to the laser as well, but that's too bad. So what happens here? So if this laser emits all the light simultaneously, and if you would only have a single detector to measure that, then you would need to move this reference mirror. You need to move that to get your signal. What you would get is a direct measurement. So you would move the mirror. So let's call that you would call that set, and you would get some kind of interference pattern that is completely random. Corresponding to your sample. You would do that a couple of times, you would average that, and you would take the envelope, and then in the end, it would look like this. And this value, this average value, you would plot on a grayscale, and that would make a pure image. And moving this mirror takes a long time. It is not easy to move components around at a fast rate. So that's why it is slow. For the spectral domain implementation, the laser could either still emit all the wavelengths at the same time. The mirror here, the reference mirror here would now be fixed, but you would have multiple detectors. So grating here, and that would split the light into different wavelengths or different wavelength bands. And they would be detected simultaneously. So you basically gain, if you have n detectors or n wavelength bands, you would gain a time of n in your acquisition. You would get the same result, but then much faster. The other option is for this part is to have the laser not emitting all the wavelengths at the same time, but have the laser emit them for one single wavelength, but then in very fast succession. So you can then still use a single detector, but because it is much faster than moving the mirror around, you would still get that same advantage. What is shot noise? So what were the different noises that were associated with those two?
Thermal noise.
Thermal noise.
Something you can get rid of if you increase the intensity of the laser.
So thermal noise is something. So from the engineering point of view, thermal noise is something if you just cool down the system, and then. So yeah, it is there, but not the biggest issue.
Then shot noise is, I think, due to that the laser is a bit of fluctuating in the amount of photons in different time frames.
Yeah. So it's a really fundamental physical quantum mechanical thing, basically, that the laser just does not emit a steady stream of photons per unit time, but it fluctuates a little bit, and that fluctuation will eventually translate into the thing that you measure with that laser. That is the shot. Then the other was intensity noise. So just to be complete, do you remember what that was? When it happened? Yeah, so background noise sounds a little bit like thermal noise, so not entirely satisfied with that answer. But no, so intensity noise happened when you would turn off the power of the laser. So if you would have it emit more and more photons, then basically you could say that the shot noise emission gets nonlinear. So it does no longer scale with the power output that you want to have, but it scales non-linearly. So there is a regime that was the graph, I think, on a log scale, when you had this regime where you could increase power without much penalty, so the noise would increase a little bit, but not that much. And then if you would increase it further, then it would increase more. So talking about the things that you can control, so the power which you want to emit your laser with, that you can control. So you can, just by turning down the knob, let's say, you can be sure that you're in this regime. And still you would have that shot noise. So shot noise limited detection means that it's basically another term for the best that you can do. Because that shot noise is always going to be there. You cannot, that is just a physical principle. You cannot different it. So yeah, so the best you can do. Do you know how the depth resolution of an OCT system is determined? What factors determine that?
Thinking about the coherence length.
Yeah, please elaborate.
It's the envelope of your wavelength and the lambda zero.
Yeah. So that would mean that if you would have this, I already erased it. If you would have an OCT system where there is a mirror, just a mirror in the sample arm. So you're only measuring one reflector, then the ideal signal. So let's say that this is the depth at which you're looking at. The mirror is positioned at Zm. The ideal signal would be just one p with infinite resolution. But that's of course not happening. So so what you will see in practice is a signal that looks like looks something like this. It will have a width, which you can characterize in many different ways. But one common way of doing that is that if this is the max, and this is the half max. Then to look at the full width, so the width of this peak in terms of Z units. At that half max in the front. And that's coincidentally, not so much, is called the coherence length of the laser. Do you know how to calculate it? Coherence length. So underlying this was an interference pattern. Not necessarily the same scale as it. And then the envelope, that is what is plotted. Do you know how to calculate this full width of max, or this width of this?
I think it's 0.44 times the lambda zero squared divided by lambda.
I'm not going to let you get away with the 0.4. So it is 2 ln 2 over pi, 0.44, times lambda zero squared over delta lambda. Okay, that's the formula. That's good. So what again? So briefly, what is lambda zero squared? Not you, someone else.
Wavelength.
Yeah, almost. So both of these are so both lambda squared and delta lambda are characteristics of the light source.
Okay, so it's the central wavelength.
Yeah, exactly. So lambda zero is the central wavelength. So so the light source would have a spectrum that looks like this. My best approximation of a Gaussian. The center would be lambda 0, and delta lambda would be
that with
yeah.
with
So the
long
width,
maximum.
so this yeah, so the width of our maximum. And, in case you wonder where this factor comes from, that is just from the assumption that the spectrum is Gaussian, and if you do that whole, if you go through that whole calculation, then this factor just drops out. It's about okay. So that would be the resolution in depth. So if you would look down, but an image, of course, has another dimension. You basically here two resolutions. The other resolution is called here the lateral resolution. So let's call that the resolution that is perpendicular to the depth direction. Do you know how that is determined? What governs that resolution? So what do you know about microscopy? Do you know what the resolution of a microscope, how the resolution of a microscope is determined? That's fair. This is a lens. There's light coming in from this direction. Somehow we managed to make a nicely parallel illumination, and then if this is the optical axis, then the light is focused by this lens onto some point, the focal point. As you know, right? So the conventional ray tracing way of drawing that would be to draw it like this. So the light is concentrated in the focal point, and then after that it diverges away. What is wrong with this picture?
Too hard, so the point it's not really the point, but that's the width.
Yeah. So you cannot physically manage to put all the power. If you would be able to put it all in one point, then the power here would be infinite. That just cannot happen. So how it in fact would look like is indeed what you say. Is so far so good, but then something like this. So where you concentrate the light is going to have a certain width as well. So now let's say you want to measure a very small point, a very small particle that is located exactly in the center of this beam of this system. How would it look like in an image? So how would this point? So this would be the just a point, would be the ground truth. How would that look like in an image? Yeah, exactly, spread out. So here we would have depth. Here we would have width. So how would that point look like? So not as a point, obviously, but as something that has a certain, so let me draw it this way. Exaggerated, something that has a dimension in the z direction, and it has a dimension in the width direction. So this was the resolution in depth, the coherence length that we just discussed, and this is then basically the resolution that is determined by the lens of the system, by the optical components of that system. If you can manage, if you replace this lens with one that focuses the light a little bit more tightly, you would get a smaller width here, and you would see a smaller particle here. Same particle with a smaller image. Yeah. Okay. Last question, and then we'll take a break. Let's say we have two OCT systems, and they are exactly the same. The resolution is the same, the speed is the same, the cost is the same, everything you can imagine is the same, except for this. The center wavelength of one system is 800 nanometer, and the center wavelength of the other is 1300 nanometers. And you can pick one of these two systems to either image the retina, naturally, so the back of your eye, or some skin condition. So which system would you prefer for any of these applications? And why, of course.
So system with a longer wavelength or the retina, you just want to go deeper than the skin?
That could be. It's not the answer yet. So go along this
Yeah,
this
I
thing.
thought maybe shorter off for the skin because that's
Okay, I see your reasoning. So what's good in your reasoning is that you think about how deep the light goes. So what determines, so especially in an OCT system where you have the situation that light needs to go in first, and then to be reflected or scattered, and then has to go back. So what determines how deep that light goes?
energy.
Yeah, but the energy is wavelength, and we had that here. So that is okay. Let me specify the question. What properties of the tissue determine how deep the light goes? Absorption, of course. If light is strongly absorbed, it will not go that deep. Is there another mechanism? Scattering. If light is scattered away, then it will never make it back to the detector. So both of these processes are important. What is the most important absorber in tissue? Water. If you answer just water on your whole exam, then you have a 7. That is 70% of us is water, and 70% of biomedical optics is caused by water. So water is always the right answer. Do you approximately I don't expect it, but do you approximately know how the absorption spectrum of water looks like for these wavelengths? Or put differently, where do you think that the absorption is higher at 800 nanometers or 39 nanometers?
So higher in the second one?
Sorry?
Is higher absorption coefficient in the second?
Yeah, in the 1300. Absolutely. And if you want to image the retina, you have to. So the OCT system is here. The retina is back there. You have to go through the eyeball. That is 2 centimeters of water on the way in and on the way back. So for the retina, you want a wavelength where the absorption by water is really not that high, because otherwise you would never get any light. So that is mainly the reason why for the retina we would choose 800 nanometers. Now for the scattering. So 70. For most tissues, it is 70% water. That would also be valid for the skin. That would also happen there. So why would you? Can you think of a reason why you would pick 1300 nanometers over 800 nanometers for skin? The spoiler is, of course, it has to do with scattering, but. So same question. How does how does the scattering coefficient, the scattering strength, compare between 800 and 1300 nanometers? Which one is higher? Which one is?
That's higher for 800 nanometers.
Yeah, there it is higher. So for skin, where probably you want to you would want to look a little bit deeper, you would prefer a lower scattering coefficient. So you have the trade-off here. So for the retina, it is mainly determined because of the absorption coefficient of water, which you have to go to, which is a lot. So then you pick probably 800 nanometers for the skin. Even though there is a lot of water in the skin, but you would want to look a little bit deeper. There it is really the trade-off between how much light do I lose because of scattering, how much light do I lose because of absorption. And then basically then the needle points to 1300 nanometer as the most efficient. All right, I had this question that was also in the slides, but really in view of the time, I'm going to skip this one. You can do that. You can do it for yourself. So let's say you have these two systems, so 800 and 1300 nanometer. You want to get a depth resolution or coherence length, as we just thought of. What bandwidth do you need? The formula was also just there, so you can try that for yourself. So I'm going to skip that for now. Last question before the break. And that is shifting gears a little bit towards actually the topic of today. These graphs show spectra, so something as a function of wavelength. So same compounds, namely hemoglobin and oxygenated hemoglobin, so the protein carrying oxygen, either loaded or not loaded with oxygen. Do you see any similarities or differences between these graphs? And do note that this is on a log scale and that is on a linear scale, so that is it's a beetje flauw. So are there any things that you notice that you say, okay, this is in terms of the shape, let's say. So I'll give so for example, here, the thing to notice is that they are different. They're very different. There is for the oxyhemoglobin, the oxygenated hemoglobin, there is, for example, around this wavelength band, there is a peak, a valley, and a peak, whereas for the hemoglobin, there is just one peak. That's a notable difference. Also, one thing to notice is that there are some wavelengths that you can identify in the spectrum where the absorption coefficient is the same for both. Now, to translate that into the graph on the right, is there anything?
The index of refraction for the oxyhemoglobin is most of the time higher than the hemoglobin.
Yeah, that's one thing. Yeah, absolutely true. Something about the shape, maybe?
With the absorption coefficient of skull and the index as well.
Yeah, that's also true. So yeah, so it's even more pronounced on this log scale that it really drops and then also drops a little. What about the peaks and the valleys? Yeah, exactly that. So if you look at this this absorption coefficient, so around 400 nanometers, there's a big peak in absorption for both compounds actually, and just so not exactly at, but just around that, there is also a big upswing in the index of refraction. The same thing you see for. So if you again look at these at this region, so for the oxyhemoglobin, there is this peak, valley, peak. If you look at the refractive index, little bit further downstream in wavelength terms, there is again this peak, value peak. For the deoxygenized hemoglobin, it is more smooth, and here we see the same. So clearly, just looking at it, there seems to be a connection. That is and that connection is the thing that I want to discuss next. But let's first have a break before we go into that, and then so let's take 15 minutes. Yeah. That's pretty silly. The last 2 years were all online, so I have to readjust my sense for timing. For it's a weird sensation. Yeah.
The assignment.
Yeah.
So in for the probability distribution, capital P of theta, we use this formula. There's this integral over from 0 to theta. Okay. So I mean, okay, I use this specific assignment. So we make the substitution. We change the cos theta for here, for x.
Mm-hmm.
Then the integral limits shouldn't be like this, like from 1 to x.
No,
in your notes you have like from
minus
-1 to
yeah.
x. So normally it should be like from 1 to x, and then with a minus sign it should become like this, right? From x to
Yeah.
1. Then the result is kind of similar. Like we get this, instead of getting the square root of R and D, we get this the square root of 1 minus R and D. It's okay.
Yeah.
It's in the previous lecture that's the same thing, because yeah, 1 minus R and D could be also goes into R and D. But yeah, I mean, it's a bit different.
Yeah.
And even the integrand limits.
Yeah, so that's where it comes from. Because so I'm not. So do you? Let's see.
That is the function.
Yeah.
The P of theta and P is that, and then we have the 2P because of the
integration. Okay. So that all drops, and then this part is also not independent. So you can also put that in front of me. That's all going to fine. So then you have 1 plus cosine theta to the power of n times sin theta d theta. And then you make the substitution. So I think you make the substitution a little bit different. So you would have something like E of theta starting with so let's assume that the vector supply is already gone. So we're only looking at theta now. So this would be the
yeah, but this is the previous step. Right?
Yeah. Okay. Yeah. I'm trying to catch up where the step was on. Then we make the substitution. Sine cosine theta is cosine theta is x, and that leads to P of x is -1 to 1.
Because here cos of 0 is 1. and cos of t is
Yeah.
-1, and then because of the minus sign, we have to,
yeah, and then you can switch it
yeah,
back.
yeah,
So,
yeah.
okay. Px, Px, dx. Okay. So now the idea is that we're not going to sample theta, we're going to sample x. So we'll get try to get the random value of x and not of theta, because we can always scale it back later.
Yeah.
So what you will get is something like a p of x, so a large capital P of x is then by the rules from -1, because that's the lower limit, to some value of x.
Dus dan moet
Okay.
die voordat je
Het kind of gives now. So
I'm not going to give away the whole answer. You understand? So instead of you're not going to sample theta itself. Instead, you will sample cosine theta, this x. You will get the random value of that, and if you ever need, so if you look at the geometry equations that are in there, it's always cosines or sines. So you almost never need theta itself.
yeah,
And if you ever need it, then you can always take the inverse cosine.
yeah. Okay, so that's why we use the -1.
Yeah.
Because it's not because of the
So it
substitution.
is just from this one. So the normalized version would be the integral from -1 to 1 of dx dx. This would be the PDF. A probability density function, the CDF, the commutative distribution function would be this. So integrated from the lower limit up until the value that we want to know. In this case, this is x. And in the end, x can be translated into cosine.
So but the limits of the integration are not like they're not changed because of the substitution. They are
No,
the
there's
same as the-
some substitutions
yeah.
that was made earlier, and now.
Okay, so I mean, we assume that the substitution has already happened in this step in the part. Okay. All right, thank you.
Ja, ik
Weer een nieuwe taal. Wil je ook physiology dan?
Nee.
Ja.
Ja.
Vind je het leuk?
Ik weet wel niet meer hoe het samenvat. Ik zag op de tentamen van Ed.
Ja.
En die eerste paar vragen waren echt heel erg makkelijk. En de tweede, die ook niet goed gekeken. Tot één vraag snap ik het antwoord niet bij. Altijd ook van, zoals werd aangegeven in de vraag, maar ik snap het echt aangegeven.
Ik heb het niet gekeken. Ik ben echt geen idee wat het voor.
De eerste vraag van de tentamen was van, je had zo'n plaatje van aders per takken. En toen was het van, ja, waarom is de druk veel lager? Uiteinde. Van het oppervlak.
Ja, maar ook echt met die mathematica.
Ja, ik dacht maar dat ik dan een keer niks weet.
Nee, ja.
Maar de opdracht van vandaag ging echt chill. Ik had in de trein al aan gewerkt. Ik had hem al helemaal opgetypt. Ik hoefde alleen maar die vergelijkingen in te vullen. En,
ja, maar dat vind ik. Dus zitten dus nu al deze hele week gewoon vergelijkingen overtypen. En dan krijg je plotjes en dan moet je de plotjes
ja, hij maakt een opdracht. Zeg maar alleen de opdracht in de stellerij. Hij krijgt foto's toe met de antwoorden. En soms mist er wel een antwoord waar je zelf in moet aanvullen en moet het aanvullen. Want zoals die heel eerlijk is, echt een beetje
maar toen was mathematica, dat tentamen, toen is er nog best wel wat doen.
Ja.
En nu, echt alles wat we doen is gewoon, echt, we krijgen een foto, een screenshot van code, en die typen we over, en dan vullen we die code, en dan werkt die, dan heb je echt een spelfout maken, en dan werkt die. En dan moet dat is gewoon, dat leef je erin.
Oh, ik had super lang.
Het is gewoon een master.
Ik zag van gisteren, ik had super lang een error. Hè. Ik had die hele code ook moeten controleren. Had ik in dat laatste stukje waar je die netberekening gebruiken. Dat was de hoofdletter. Gewoon mijn hele code klopt, alleen je aanroeping was fout.
Ja, echt, ik heb iemand zo belangrijk.
Ik ben wel echt wel, want het wel echt.
Volgens mij gebruikt Ivo het, want daar houdt het dan op.
Vast wel ergens, maar dan... Ja,
ik vond het bij wiskunde wel chill als je van die zieke SERPs integralen had. Dat was gewoon fijn.
Redelijk nuttig.
Je bent na wiskunde 1, 2 nooit meer tegengekomen.
Ik heb het aan hem gevraagd, want dat zit anders. Hij zei, jij kunt ook niet corona gemaakt over. Dus we gaan vanmiddag gaan gevraagd, maar misschien dat ik het nog lokaal en gewoon. Maar weet niet zeker, maar dat zijn we. Ja.
Ja. Zero.
Hi.
Ik kan bij de beide laten zien. Ja, ik had het niet geholpen.
Precies, dat je afkomt. Kom blijven. Die zijn niet. Dat is gewoon normaal doen.
Dit is niet normaal.
Nee.
Al waren het een beetje met
Nee, wij zaten er bij elkaar.
Ik zat op de aflaat.
Oh, wat dan?
Oh, oké, dus dat is
Dat is een
ja. Alleen weet niet.
ja.
Ik weet dat het op regel, maar zeg dat je bij ons kopen doet. Zo, stel daar zo maar blij. Oh, is dit? Nee, dat is natuurlijk. Ik heb hem hier, het staat in de weg. Oh, het is mijn boom en klant.
Hoe is het weer van? Wat kan ik hier doen?
Je kan het presentatie en ja, bij
Okay, guys, I'd like to continue. So one of the titles of today, of the topic of today was causality, and of course that is a very old classical principle that I'm not going to read that out loud because my Italian is probably much worse than yours. Basically, the physical principle is that the effect cannot precede the cause. There has been some debate about this causality principle. First. So, for example, so the practical example for optics is that if you excite light, yeah. So this is a little bit the part of the presentation where there are corny slides. So excuse me for that. But the example is that if an electromagnetic wave hits a medium and light is scattered, for example, and the scattered light does not occur before that stimulus. And it also implies that the response, so the scattered light, cannot travel faster, in this case, than the speed of light, because otherwise it would be before that. The implications of this causality principle given a lot of thought in the early 20th century by Heisenberg, which you all know from his uncertainty principle. Yes, he was. He formulated it in some way that okay, so if we know the present, we can calculate the future, but the other way is. But it's not entirely right because you can never know the present. That is then the uncertainty that was in there. So people were philosophically and mathematically thinking about this principle a lot. This is just a fun question to see. So you're physicists, so these are all old white guys that did a lot of physics a long time ago. Do you recognize any of these? You don't have to. I'm just curious. It's an old conference in Copenhagen in I think 1918 or something. And basically, so 1918, the early 20th century was a little bit of a heyday for the physics community, and a lot of developments came through. So there's a lot of now famous names from your textbooks sitting in these benches, just like you are now. So, do you recognize any of them? Nah, that's okay. That's okay. So these were the names I've highlighted, the ones that are a little bit better known. So Pauli, from Pauli Verbod, so that's all good. We have guys here. Niels Bohr, of course. Klaus and Turner, I will get back a little bit later. Paul Heerdekerst, You will also see that there is somewhere some, where is he now? Darwin in here. But there you go. That is not Charles Darwin, that is his nephew. Yeah. So apparently that ran in the family. But the two I want to talk about, and I've alluded to that a little bit, are the Kramers and Kronig for the relations that they developed. So these are, if you ever encounter a statue of them, I doubt it, but you never know. Kramers and Kronig. So let's look at this principle of causality. The effect cannot precede the cause. So how do we describe that mathematically? Well, using this kind of equation where we have a response to a physical system, so something that responds as a function of time. There is an input, an impulse, that can be the kick to the ball, or that can be a prolonged oscillatory stimulus, that can, whatever you like, but it also has a function of time. And there is a response function, a causal function, a function that basically relates the output to the input. Do you recognize this integral? Shape of this integral? So, Convolution integral, exactly right. Are you familiar with it? So no, not much. Okay, so if you would try to explain this integral. So look at the properties, look at the boundaries, look at the arguments. What do you notice? What do you see? So on the left-hand side of this integral is the response at a certain time t.
And then kind of shift from that certain time to another.
That is maybe what the input does. But what does the integral itself do? So what are the boundaries? Yeah. What does the integral do?
Calculates the area under the function.
Yeah, it calculates the area. It sums up things. It adds things. What this integral says is that the response at a certain time t is the sum of everything that happened before that time t. So the upper boundary is t. So everything from time everything from time 0 when the impulse started to times up until time t is added here in the response for that. You're right, it is a convolution integral. A convolution means that you have a function x, let's say a function f of x, and you multiply that with a function g of x minus x prime, just like it is written there, and you integrate that whole. But we'll get back to the convolution. But the idea is here that, and again, that is really important idea that the value of the response of the system at any time t is not just given by whatever the input is at time t. It is given by the history, by everything that is being put in from 0 to t itself. Is that clear? Is that a good way to look at this integral? Then we can continue. So that function z, that is the function that ties it all together. That is the function that translates the input to the response. It is then called a causal function because
Please draw maybe can make a drawing to make it more visual. I mean, I don't see how the graph looks like, for example.
How the graphic looks like.
Convolution.
Yeah, okay, that's a good question. Can I pause it for a little while because I have a graph a little bit later on. If it is still not clear then please ask again. Is that okay?
Yes.
Okay. So for now, what we'd like to note is that so the causal function z of t is is what would tie that together. That would tell you how a certain input at a certain time t accent translates into the output at time t. So that would be z of t. You can take, of course, the Fourier transform of that function z of t. You will get z of omega. That's frequency, and that would be a complex function. Does that also make sense? What does that imply? Do you have any idea also? So what is the okay? Let me ask the question in a different way. So what would be the characteristics of a complex function? And so here it is written as a real and imaginary part. So that is not the answer I'm looking for.
That's a phase.
A phase and an amplitude. Okay. So what does that mean? What does that amplitude mean in this case? So think of a response function. Yeah. So okay. Think of an electric circuit. I have an electric circuit. I don't know how to exactly. I put on a certain voltage, and I measure at the output again a voltage, and that will not be the same. So the amplitude can be different. So there's amplitude. What's the phase then? Okay, so let's say I put a sinusoidal. Let's say I put a sinusoidal pattern onto that same circuit. I would get on the outside also a sinusoidal pattern because I assume that the circuit is linear. The amplitude will be lower because it's more or less what we assumed in your answer, or higher, who knows. But the oscillation can be different in phase from the input. That's the phase. That is the phase. So basically, you have a system, a physical system. You apply let's say an oscillatory input with some frequency and some amplitude. On the output, you get a different amplitude and some phase difference, some phase lag, and that is what this response function describes. If you describe it as z of t, then it is a real function and it is just in the time domain. If you take the Fourier transform, then it has a real imaginary part, or more cleverly, probably, it has an amplitude and a phase. So that's now the whole promise or the whole implication of these Kramers-Kronig relations is of causality is that there is a connection between. So if you write it this way, there is a connection between the real part and imaginary. Of course, that also means that there's a relation between the amplitude and the phase. It is only a little bit more difficult to express that. Just because it is a causal function, just because we describe a response to a system which cannot occur before the input, there is going to be this relation. We can do that for the complex refractive index. So the refractive index, we briefly touched upon that earlier on. It was in the description of Rayleigh scattering, for example, N, you remember? We describe how strong it scatters. There is also an imaginary part. We'll get to that in a moment. And the Kramers-Kronig relations connect these two. And of course, and this is again the corny remark, so I'm sorry for that. And that makes the refractive index the one property to rule them all, because you can use that to describe both scattering and absorption. Up until now, I've treated them a little bit as two independent properties. So you can have light loss due to scattering, you can have light loss due to absorption, but actually they are related, and the way to relate them is with the refractive index. Okay, here we go. This guy, you know. These are Maxwell's equations. I am pretty sure you're able to derive the wave equation from this one. You at least you had this in some course, right? Okay, that's good now. So just to be sure, E is the electric field strength, B is the magnetic flux density. We have the permittivity here, epsilon. What is it? And the permeability, the magnetic properties over there as well. So important thing to know. So this is something that you put in and you get out. These are the material properties. So the permittivity and the permeability. Using all these clever substitutions, taking the curls and doing the second derivative, etc., etc., you can turn this into a second-order differential equation for the electric field, which is called the wave equation. So you have something that has. So what's nabla again? So what is the, this is a derivative to time, right? What is nabla? Yeah, derivative to spatial coordinates, and because we have 3 spatial coordinates, it is a little bit too elaborate to write that down. So this just means nabla just means a derivative to each of the spatial coordinates. And if you have a nabla squared, you do it 2 times. That's what it is. Okay. Link for the nice derivation. The simple way to try to solve these kind of equations is just try something that is harmonic. So try sine and cosine functions, which would represent a traveling wave in space and in time. So you could write something like that is a vector times a cosine plus a vector, another vector C2 times the sine with the arguments as given there. K is the wave number, we can count that. 2 pi of lambda the wavelength. And a propagation, sorry, a propagation velocity v in this case. Again, this expression has sines and cosines. So with certain wave vectors. So it means that it has amplitudes, C1 and C2, and it has phases, whatever is in the argument. So even though this is not a complex representation of the electric field, it already does suggest that we can write the electric field in a complex way. So as something like an amplitude times the exponential of imaginary times. So already by using sines and cosines here, we impose or we include the possibility that it is complex and has an amplitude and phase. Okay, now let's regroup this a little bit so we can bring K into the brackets. So K times R plus or minus K times T times T. And rearrange a little bit. So introduce, in this case, introduce a new symbol. Where if you compare or if you connect these 2 equations, we have an expression for the velocity of the wave, the traveling velocity of the wave, the propagation velocity of the wave, omega over k, so the circular frequency of the wave number, equals, in this case, if you fill it in the wave equation, if you solve it, then you will, then the answer you will get is 1 over the square root of mu times e. So the square root of the permeability times the susceptibility. I'm not going to dwell on this. You can look at this yourself. Point is, the important point is that the velocity of the wave in that medium is determined by these material properties, by this permittivity and permeability. So how fast an optical wave or an EM wave travels in the medium is given by these properties. So what we usually do is split these into absolute and relative properties. So absolute would be the values for vacuum, and relative would be the values for a material. So epsilon 0 and mu 0 would be the values for the vacuum, and the ones with the subscript R are for the material. We can rearrange this whole thing. So this absolute velocity in the medium can then be written as a value that is valid for vacuum, that is C, and a correction factor, if you like, for the material that is given by M. For the wave, electromagnetic wave velocity in the medium, we have a symbol, that's C, speed of light in vacuum. You know that, it's 3 times the 10 to the power 8. And then for this M, so basically the 1 over the square root of the product of the relative susceptibility with relative permittivity and permeability. That is also a different quantity. That quantity is called, you know? What is that quantity called? So the blue in blue. So this basically defines the speed of light in vacuum. Yeah, it's all that's only a material property. Yeah, that's the refractive index. That is the refractive index. So just from Maxwell's equations, from going down from the wave equation, this is the refractive index. I cannot stress enough. I'm going to do it now. It is not a constant. So it is a material property, that's for sure, but it's not a constant. It is a function of omega, of the frequency. It is a function, therefore, of the wave number. Okay, it is a function of the wavelength. So whatever way we express it, there is never a fixed value. It will change with wavelength. Yeah, just to briefly to drive this point home about the solution to the EM wave equation. So they are, if you look at the solution, the electric and magnetic fields are in phase but are perpendicular to each other. So that is what the cross here signifies. That is the outer product of vectors. So E cross B is an outer product, and they are and that outer product is in the direction of propagation. That is in the direction of the wave vector K. So if the EM field, or if the travels in this direction, then we would have, for example, an electric field that is perpendicular to that in this direction, and a magnetic field that is perpendicular to that in that direction. The magnitude, so these are vectors. You can calculate the magnitude. That's familiar wave with K, so pi over lambda, related to the color, to the color. If you look at an EM textbook, then you will see that what the previous slide described was actually the Poynting factor, the factor that describes the transfer of energy per unit time or per unit area, something like that. We already saw this a little bit earlier on in intensity, so I'm going to use that a little bit indifferently for that. If you now look at an expression, so you take the outer product of the electric field and the magnetic field, multiply that with the appropriate scaling factor. Again, I'm not going to go into that. We can calculate the energy, or the energy transferred, or the intensity, the watts that are contained into that EM field. Just to give you a little bit of feeling for the numbers that we have. So if you would the step I'm skipping here is that the electric field and the magnetic field are proportional. The magnetic field is much less in strength than the electric field, so we can usually factor that out so that the intensity is going to be proportional to the electric field squared, and that's possible. We'll stick to that. If you look at the intensity, for example, of the sunlight on the surface of the Earth, that is about 1 kilowatt per square meter. If you look at the intensity of moonlight on a bright night, then it's about 2 milliwatts per square meter. So these are basically the numbers that occur in natural environments. So do you know what you can reach with a laser? Okay, can you think of what you can reach with the laser? Yeah, megawatts. So just by concentrating all that power into a small spot, if you have a small beam, or if you can focus that a little bit further, you can go to megawatts easily. Okay. So just to be clear on the ways that we write intensity and electric field. So usually the expression is going to be that the intensity is proportional to the electric field squared. I'm going to use that a lot. Sometimes I need to average a little bit, so then the brackets occurs. And every now and then we need to consider that the electric field is actually a complex quantity, so with an amplitude and a phase. This formulation of the square will appear, so where E is multiplied with the complex constant. All right. So then the question is, a solution to Maxwell's equation was a plane wave that traveled into the direction given by K. So the expression is given there. If we now know that the refractive index is a complex quantity, there's an amplitude and a phase, it is by n, or real imaginary part, by n. Can you now, just by substitution, can you now write down what the final expression for the electric field is going to be? Then the second question is, knowing that, what is the expression for the intensity? So it's a very short question, I think. Yeah, so R is see if I can write the geometry right. So let's say you have a scatterer here. Then I'm actually not sure if the inner product should be there at this moment.
I think that's right.
Yeah, I think it's right as well. But I think it's right, but I'm not.
Yeah, I was just wondering if they could be parallel, so we can just.
Yeah, they can be parallel, but if they are not, then it means that R is usually R is the direction of observation. And then K is the direction of traveling, of scattering. Yeah, so that's what it means. So K inner product R tells you how much you will observe here from the light that is traveling in this direction. Yeah, that's it. Okay, so what happens if you would fill in this expression into that exponential term?
So the imaginary part, no context of
Yeah, so yeah, exactly. So you would have so you would fill in something that is real and imaginary into the exponential. It's multiplied by e. If you multiply the real part with e, then of course it becomes an imaginary part. If you multiply this part, e times k with minus 1, it becomes real. So you get two factors. You get two exponentials. One that is still a complex exponential, so still an amplitude and a phase, so that is still an oscillation, and one that is a real exponential. So it's damped. It decreases with in this case with the distance. So if you look at the amplitude of the electric field with distance, it will decrease. If you then square that, so conveniently now take the square and then take the amplitude, then or multiply with the complex conjugate, and then you can also do that. Then the oscillation part vanishes, but the damping part remains. So you would have what you will end up with is an expression that looks like this: on amplitude times a real exponential damping. So K here is again the imaginary part of the complex reflective index. Of course, this one looks a lot, quite a lot like Lambert-Beer's law. Exponential to the power minus mu a times L or times RL. So, in other words, what we arrive now is a electromagnetic way from Maxwell's equations to define an absorption coefficient. So mu a, so the damping coefficient of that exponential is directly related to the imaginary part of the refractive index. That is that's the important concept. So K is again is the wave factor. 2 pi over lambda. Kappa is the kappa is the imaginary part. Omega is the frequency, which is related to the wavelength. So this is it's a wavelength dependent property. So it will vary with wavelength, and it defines an absorption coefficient. So now let's look at water. Again, one of the most, or maybe the most important absorbing properties of in tissue. So we can write down all these three equations for the absorption coefficient of water. We can measure the absorption coefficient of water in a cuvette using Lambert-Beer's law, and then we can write, or we can express the imaginary part of the refractive index like this. So as a function of frequency, or as a function of lambda, or wavelength, whichever is more appropriate. Okay. So basically we tied one of the optical properties, one of the important optical properties, the absorption coefficient, now to the complex refractive index. That is what this equation here measures. The point that I want to get across today is that because of causality, that the real and imaginary part of the refractive index are related, or more formally, are not independent. Which also implies that now by this equation that we now have, that the real part of the refractive index is not independent from the absorption coefficient. This is what we will arrive at, this expression. So something or an integral expression that says that the real part of the refractive index is related to the absorption coefficient. Again, with a complicated integral, so that's something that we'll work on, but this is what we'll end up with. That's too bad. It requires a lot of math. So my proposition is that I will just start. Halfway we'll take a break, and then I'll continue. I've also posted. I've recorded actually the coming part, so that is also on Canvas. So if anything is unclear now today, then hopefully it is a little bit clearer in the video or the other way around. Thanks. Okay, so then you already know it. So I think I'm going to help ask for your help. A little bit long. So now the graph that you asked for. So let's say we have again this causal function z of t that describes the response of the system. So R is the response in terms of the input t. So this is the graph that I was trying to reproduce. So we have an input that could be a kick or something that is a little bit prolonged, but at least in red. And then the system, the physical system, responds to that by some measurable output. And that is given by R. So we can define that the input. Define our time base, so the input starts at t is 0. But it may last longer. It can be a prolonged excitation. At least the fundamental requirement of causality is then that the response does not start before that. So that also, so if the input starts at t is 0, then the response at minimum also starts at or at r of t is 0. If t is less than. So that is what's in the graph. Is that an answer to your question? Or yeah, okay. So mathematically, we would express it like this. So R of t is given by whatever value of e happens at t accent, times some function, which is clearly not defined in this case, but something that ties the input and the output together. Did you have a course on electronics, for example? Yeah, so you had this some RC circuit. What's it like? With a resistor and a condensator somewhere there. So you could express. So if you would put in an oscillating voltage here, you could. Scattering is also in a way again. So with a resistor and a capacitor. Sorry, that's the word. A capacitor somewhere there. You could calculate if you would put some voltage in here, how that voltage V out would look here. Yeah, or no? Maybe a little bit. No. Okay. Okay, but let's not get into the specifics of this. The point is that this is an input. This is an output. V out is an output. V in is an input, and the response of the system is what defines that function z of t prime in this case. So how the so in this case, if you would, so just dwelling a little bit on this case for a moment, if you would define a sinusoidal input v into as a function of time to this system, can you imagine how the output would look like? Not entirely, I think. So, trying to get to your inner engineers here. So, okay, we're getting a little bit diverted, but okay, that's the fun thing. So what happens here? So you put a voltage here, so there is charge flowing into the system. What happens here?
Also get an oscillation and an output, I think.
Yeah, so it's a little bit resisted because of this resistor, but in the end it will charge this capacitor, and because you have something that detects it here and output there, charge will also flow to the output. So what you will get is probably something that has that is also an oscillation, but then with an amplitude that is a little bit less. I'll draw it just in a moment, a little bit less because of losses basically in the system, but also it lags a little bit because it takes time, because of this resistor, it takes time to charge this capacitor, and it also takes time to decharge it again. So you will get an output that it's going to be difficult to write on the same to draw on the same scale. That is less in amplitude and a little bit lagging in phase. And the function that ties that together, so I don't know by heart, I'm a little bit ad-libbing here. I don't know by heart what the transfer function for this circuit is, but the function that will describe that in time is this Z of t. That's the point here. And you can do that for any system, for any linear system where you have an output, where you have an input. If you know that, you can write an equation like this. It's not going to be easy, but you can do it. That connects it. Okay, this is like you said before. This is a so-called convolution integral. So convolution is where you take one function, you multiply it with a shifted version of another function, I of t, but then shifted and you integrate it over the shift. That's what the convolution does. Okay. Now let's take the Fourier transform of both sides. So R of t becomes R of omega, and then this integral simplifies to a product. Have you seen this before? It is the so-called convolution theorem, that if you have two functions that you convolve in the time domain, then in the Fourier transform domain, you are allowed to multiply their Fourier transforms. So Z of t would give a Fourier transform Z of omega. I of t would give a Fourier transform I of omega. And this integral in the time domain corresponds to a this convolution integral in the time domain corresponds to a multiplication in frequency. Have you seen this before? Okay, then for now accept it. Look it up. It is. I'm sorry if I did not realize that. Otherwise, I would have spent a little bit more time on this. So the function Z of t is real. So what does that mean? If it's real? That's not complex. That's one thing. So no, it is only an amplitude. So it's only basically it only tells you, yeah, how it responds how the response is at a given time. So nothing. But the complicated thing is that even though the function Z of t may be real, then the Fourier transform can still be complex. So.
Does that mean that you only have guarantees on certain?
I'm not sure if that means that. No, it just tells you that that given an input at a certain time t, can be shifted. You can you can calculate how how that translates into the total output. And that can een beetje ontwikkelen hier. That can translate into a difference in amplitude and phase, which is expressed in the complex part, but not entirely clear in the real part. So the same thing holds for the Fourier transforms of the response function and the input function. So to put it in another perspective, if you describe something in the real domain, in the physical domain, so where things actually happen, then it is then we're dealing with real functions. So no. Yeah, maybe that's a good way of putting it. Then there's all numbers, and if you so the complex domain is a bit more abstract, and there you can really numerically split between what is the amplitude response, what is the phase, and what's the phase response. Okay, so let's apply a trick. So we know that z of t, the response function, is a real function. We also know that z of t is 0 when t is less than 0. So there is no, in the build-up of the response, there is no values when t is less than 0. And an additional assumption is that if z of t goes to 0, so if there is no translation anymore, then in the end, the signal itself will go to 0 as well. We express that as if zt goes to 0 as t goes to infinity. So if you kick something, you kick a ball, and after a very, very long time, the ball will stop. That's the assumption. Mathematically, that means that, so these conditions mathematically means that the function z of t is a square integratable. Okay, follow that as word. Okay, so let's now take z of t and multiply it with so-called heaviside step function. Do you know that one? The heaviside step function is a function that is exactly 0 for t is less than 0, and it's exactly 1 for t is larger than 0. So some kind of Billing function, like this sketched here.
Quick question.
Yeah.
What exactly does t smaller 0 mean up there? Is it like a condition for any of the other statements, or?
No, so yeah, that is not really well written. So what it says is that z of t is 0 when t is less than 0. Right. And z of t goes to 0 as t goes to infinity. That is what the equation says. Okay, so under these conditions, it does not matter for z of t if you multiply it with this heaviside step function. So we would just multiply it with 1 just over the range where it is valid, and with 0 over the range where it does not exist. So that should not matter. Then by the linearity of Fourier transforms, that means that these Fourier transforms should also be 0. So the Fourier transform of the original function should be the same as the Fourier transform of the function multiplied with this heaviside function. So can do some math here. We can just write how the Fourier transform of z of t would look like. So that is just this definition. So the integral from minus infinity to infinity of z of t times a complex exponential. So that's all in good. Do you know what the Fourier transform of the product of two functions looks like. If you encounter that. So you have one function, you take a Fourier transform, you get an answer. You have another function, you take a Fourier transform, you get another answer. But what now if you would first multiply these two functions and then take the Fourier transform? Have you seen it or not? Okay. Again, this. So again, this is given by a convolution. So the Fourier transform of the product of two functions is given by the convolution of the two Fourier transforms. This is the symbol that signifies convolution. And if you write this down, so again as a convolution integral, so z of t would transform into z of omega. H of t would transform into capital H of omega as well. But the convolution means that we have to shift one of them, then integrate over the basically over the whole domain that we have available in this case. So from minus infinity to. So this would be the expression for the. Yeah or nay? So if you take a look at the right-hand side of that equation, then it has the Fourier transform of that step function, h of omega, that we can look up. That is just Wikipedia, so that makes life a lot easier. It's given by this expression. H of omega is half times delta omega plus the imaginary part of 2 pi, 1 over 2 pi times delta function. What happens if you put the delta function into an integral?
So just one number.
Yeah. Okay. So let's fill this in. So that expression for the Heaviside function into the convolution integral. So z of omega remains here. The delta function, we have to shift it over omega prime. So that's what we do here. And the imaginary part is given there. Then, like you said, this delta function only selects the argument of the integral, so that basically, for that part, we'll basically cancel the integral, and the imaginary part will stay the same. So the expression, the final, the expression now for this convolution of Fourier transforms is half times z0. So that is the selection property of the delta function times an integral that remains with an imaginary component of z0 as well. Okay. So we did a few manipulations. So the first result was that there was no difference if we multiplied z of t with this step function, then that did not change the function. So that implied that these two Fourier transforms would be the same. So now the result is that so on the left-hand side, the Fourier transform of z of t is z of omega. On the right-hand side, what we just derived here, z of this product, is this a little bit more complicated expression. And these two should then be the same. And as you can see, there is a z of omega on this side, and there is z of omega on that side. So we can, of course, bring these two together and end up with this expression. So a relation between or a complex, let's say a complex integral relation for the response of a system. So z of t again was the response function of the system, and now here we have an expression that that basically links properties of these of this response function together. Of course, this is by no means usable, so we have to go on for that a little bit. But I think for all of our sakes, it's good to have a little break now. So let's.
Are we still finishing at 5 or?
Yeah, I was thinking about, so that's why I'm a little bit distracted. I was thinking about how to do this, because I have more slides than there is time. So there's a couple of options. Okay, let's do it this way. There's a couple of options. I have recorded this part, so I can go on for a little while, or you can look at if you have not already done so. Look at the recording, and we can pick it up next time again. So I'm up to both. But the honest answer is that the next couple of slides is going to be more math.
But, I mean, I have to leave just after 5, so yeah.
Yeah, but if you now take a 10-minute break, then it's almost 5. So that is. So we can also. I'm also fine with an kind of agreement that you watch the video. I really do that because that is then your homework, and then I have a few questions at the end. We can start with them next time, and then pick it up there. That's also fine with me. Yeah. Okay. Let's do it. Let's do it that way. I will. Yeah. Okay. That's good. See if the people online are also in agreement. If they're still there. Yeah. Just out of curiosity, so I had the BMO people yesterday, and they had a very long session in the morning, and then had something like this in the afternoon, and they were also really tired out. So how does your schedule look like on these days? So do you have?
The same. We had also this morning a lecture.
Yeah.
It's the last time. Yeah, it is last week.
Okay. 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 So that's good. Yeah, I mean, so it's not my intention to really wear you out, of course. So.
Yeah. Yeah, this is starting from next week. Yeah.
And on the Fridays?
Yeah, Friday is the last time that it's. Yeah.
Okay, so next Friday is going to be a little bit hard, and then after that, okay, God, it's good. And
I think that Tuesday we actually have a test in the morning, and then in the afternoon we have to.
That's not much.
So then it's 3
Monday and then Tuesday. Yeah.
Okay. Okay.
Sure. Yeah.
Programmeren is tegen je eigen tijd.